Okay, so hello everyone, and welcome to Recitation 4 for section 03. Once again, I'm recording this because all my stuff got wet because I forgot to close my bag when I went out into the storming rain this morning, and yeah. So, once again, my email is as follows. My office hours are from 3 to 5, and the topic of today's recitation will be direct proofs. So direct proofs are essentially the practice proof that utilizes direct derivation of the result that we're trying to prove, or by direct counterexample or example. And basically, in different circumstances, you can apply different techniques to directly prove something. And so, if you have it as a central statement, what this is basically saying is that there exists some element X that satisfies a proof. And to prove that there is some element X that satisfies a proof within a set, you just have to provide the element. So just provide an example, and this is direct proof by example. And similarly, we can also prove the negation of basically proving that a universal is false by the same way. By proving the negation of a universal, which is an existential, this is direct proof by counterexample. And also, if we're trying to prove a universal statement, we have to construct some derivation of the statement directly into what we're trying to prove because you have to make sure that it is general enough to cover all elements of a set. And so, yeah, by constructing something that applies generally for all elements of the set, that's how you prove universal. And I do understand that this is kind of abstract, and so let's jump into the problem statements. And here are some steps toward writing proofs, which is basically be concise. Always make sure you start out with proof and copy the problem statement. Make sure your proofs are grammatically correct, explain every single steps and include all necessary equations, and then derive the conclusion. So for problem number 4, prove that there are integers m and n such that m is greater than 1 and n is greater than 1 such that 1 over m plus 1 over n is an integer. So we have to consider just some example such that it does result in an integer, and if we just eyeball 1 over m plus 1 over n, we have to eyeball m plus n is divisible by mn. And actually, the only example case is m equal to 2 and n equals to 2, in which case it adds up to 1, which is an integer. So officially, you write proof, consider m equal to 2 and n equal to 2, which is clearly an integer, which proves the existential. For 9, we also have to prove that there is a perfect square that can be written as the sum of two other perfect squares. And the proof would once again to give an example. And actually what this question is asking is about the Pythagorean triples. So A, B, and C, integer solutions to this system. And the most basic example of this would be the smallest Pythagorean triple, C equals to 5, B equals to 4, A equals to 3. So it would be proof, consider these numbers, since c squared equals to b squared plus a squared, 25 equals to 16 plus 9, the claim is clearly true. So now we have to disprove a statement. For all numbers a and b, if a is less than b, then a squared is less than b squared. And to disprove and universal, we have to just provide some element where the negation of this is true. We have to give some element such that a squared is greater than b squared, where a is less than b. And so all we have to do is find, say, for example, a negative number such that the magnitude of a is greater than magnitude b, and a is less than 0. In this case, we can simply provide proof let a is equal to -4, b is, let's say, 2, a is less than b, but a squared is greater than b squared. So this claim is clearly wrong. Similarly, for problem 15, we have negative a to the nth power is equal to negative a to the nth power. And these might look similar, but order of operations determine otherwise. This is essentially the same thing as negative a to the n is equal to negative a to the n. And this is not the same thing. This is negative 1 times positive a to the n, while this is negative a to the n. And a direct counterexample would be, say, let n equal to 4, then this would be negative a to the fourth is equal to a to the fourth, which is clearly not true, because in this case, it would be the negative of a to the fourth, and a positive is never equal to its negative. And we can also extend this generally to say that if n divides 2, or if n is even, then this is never true, because if an exponent is an even power, regardless of which, this is always going to be positive, but this is always going to be negative due to order of operations. Hey, Hayden. I'm just currently recording something right now, so I hope you don't mind.
I'll be quiet.
Yeah, that's all right. Thank you. For problem number 20, it says rewrite the statement with the quantification implicit as if something, then something, and write the first sentence and last sentence of the proof. When it says that write the statement with the quantification implicit, it means that if it is given in for all or there exists form, you have to write it in some way that it doesn't use that. And so we can rewrite the following statement as, say, if we're given that for all integers m, if m is greater than 1, then 0 is less than 1 over m less than 1. We can say if an integer m is greater than 1, then 0 is less than 1 over m less than 1. And this wording saying that if an integer m kind of implies that m covers the generality of the set of integers. So this is the same thing as saying for all integers m. The starting point of this would be to write proof. Suppose we have an integer m such that m is greater than 1. And the ending would be the conclusion that we're trying to show, which is we have shown that if m is greater than 1, then 0 is less than 1 over m less than 1. For problem 35, we have to prove that the following statement is false. There exists an integer m is greater than or equal to 3 such that m squared minus 1 is prime. So we have to prove the following existential statement is false. There exists an m greater than or equal to 3 such that m squared minus 1 is prime. And disproving a statement is false is the same thing as proving its negation. So the negation would be for all m greater than or equal to 3, m squared minus 1 is composite. The way to prove universal statements would be to construct something that applies generally for the set of all integers greater than or equal to 3. So we can directly see that m squared minus 1 is in the form of difference of two squares, and we can factor this as m plus 1 times m minus 1. But the definition of a number being composite is such that it has more factors than just 1 itself. So case 1 would be m plus 1 is 1, in which case m minus 1 is negative 1, because m plus 1 is always 2 greater than m minus 1. In this case, this results in negative 1, which means that if negative 1 is equal to m squared minus 1, that means m is greater than 0, but 0 is less than or equal to 3. So this does not apply in this case. The second case is that m minus 1 is 1, which implies that m plus 1 would be 3. So if 1 times 3, which is 3, is equal to m squared minus 1, then that implies that m is equal to 2, but 2 is also less than or equal to 3, which means that this does not apply. So for all m greater than or equal to 3, we have that the factors in which, if it is factored into the form m plus 1 times m minus 1, then both of these factors are always going to be greater than 1. So we have proven that m squared minus 1 can be always factored into factors that are not 1, which means that m squared minus 1 is always going to be composite for m is greater than or equal to 3. So for problem number 38, we now have to find a mistake in the proof that they provide us. And the theorem says that for all integers k, if k is greater than 0, then k squared plus 2k plus 1 is composite. And the proof is that they're essentially saying if k is equal to 2, then the statement results in 9, which is a composite number because it can be written as 3 squared. The mistake with this is that, once again, this is an universal statement, and it's same for all integers k. You cannot prove a universal statement by example, because that only gives one example of an element x that is an integer, which the claim is true. But it doesn't cover all general cases, like say what if k was 5 or what if k was 10 and such. So once again, with universal statements, you have to do so by direct proof by construction. And the correct way of doing this would be to recognize that k squared plus 2k plus 1 can be factored as k plus 1 squared. And therefore, by deriving k squared plus 2k plus 1 into the form of a perfect square, we have proven that k squared plus 2k plus 1 is always composite. And actually, the unique case with this, okay, what if k plus 1 is equal to 1? That means k has to be 0. But the statement says if k squared is 0, so k cannot be 0, so that does not apply also. Similarly, for problem number 39, we have to find a mistake with the proof that they give us. So, essentially what it's saying is that I'm just going to go through this really quickly. If you're given an odd integer n, and you define it as 2k plus 1, and you define m as 2k, then the difference between them is just 1, because 2k's cancel out, so m minus m is 1, which is an odd integer. The issue with the statement is, once again, that even though this looks like it is applying some generality to the definition of n and m, it's not actually, because we have to provide for all odd integers n and for all odd integers m. And the issue is that both are defined with k, with the same variable. So essentially, if you set n to be some odd integer, which can be any odd integer, which does cover the scope of all odd integers, you're restricting m to be m minus 1. Essentially, which does not cover the scope of all m. And vice versa as well. If you say pick a certain m, you're also restricting n to be m plus 1, which is basically a proof by example, just basically 1/2 of it almost. So you cannot do this. The way to do this would be to define n as equal to 2k plus 1 and introduce an alternative variable that is not defined yet, such that it can still be generally covered. So you can define m as, say, some integers like 2x, and say m minus m would then be equal to 2 times k minus x plus 1. And we can define k minus x as some integer, say like j, to j plus 1, which is clearly in the form of an odd integer. And that would be how you would actually prove 39. So for problem number 54, we now have to determine whether the following is true or not. So for all integers n, we have to determine whether or not 4 times n squared plus m plus 1 minus 3n squared is a perfect square or not. And this is not particularly apparent just by eyeballing this if this is a perfect square, because this is a polynomial with coefficients. So let's test out some values. Say if n is equal to 1, 4 times 3, 12 minus 3, which gives 9. And that is a perfect square. For 2, this is 4 times 20 minus... Wait, no. Oh, 4 times 7 minus 12, which is 16, which is equal to 4 squared. For n equal to 3, this is 52 minus 27, which is 25, which is 5 squared. We can see that this general pattern seems to imply that this term simplifies down to n plus 2 squared somehow, if we keep going. And so now we have a hint. Let's actually derive this. So we have 4n squared plus n plus 1 minus 3n squared, which is essentially the same thing as 4n squared minus 3n squared plus 4n plus 4. Or this is n squared plus 4m plus 4, which can be rederived as n plus 2 squared. So we have shown that 4n squared plus n plus 1 minus 3n squared is in the form of a perfect square. And in this case, this statement is indeed true. So that's all the problems in section 4.1. For section 4.2, the first question is actually in a different form. So we have to now write a repeating decimal as a rational number. And while this doesn't directly relate to proofs per se, I think this is just a example or like a technique that in number theory that the professor just wants you guys to know. And so, yeah, any repeating decimal can be written in the form of rational number. And if you guys don't know yet, rational numbers uh, can always be expressed in the form of q over p, or wait, p over q, where p and q are in simplest forms. Well, they don't have to be, but let's just define it as such. They're in simplest forms, and p and q are integers. So the trick to doing this is to use the repeating part to get rid of itself, essentially. And so if we see 5, 4, 9, 2, 4 repeating, etc., the 924 part repeats as well. Alternatively, you could also use 492, but this is just what I used when I did the work for this question. So for simplicity case, I'm just going to use 924. So you first separate these two into parts, and you can write 320.54 as 32,054 over 100. Because what you can do is move the decimal point over twice, and that would be the same thing as dividing it by 10 to the number of places you move the decimal by. So this is this part. Now you can say let the repeating part be some value x is equal to 0.00924, 924, so on and so forth. And the trick here is that you want to manipulate x by multiplying by a power of 10 or shifting the decimal point right enough places such that you get a whole integer part, and the repeating part happens exactly after the decimal point. So while I get this might be confusing, it's going to make a lot more sense once I do it in practice. So we want to move the decimal points to the first part here because we want this to be an integer part, such that the repeating part 924 happens immediately after this point. So to do that, we need to shift this 1, 2, 3, 4, 5 places, or such that shifting a right is the same thing as multiplying by 10 to the fifth, or 1, 2, 3, 4, 5. 100,000x is equal to 924.924 repeating. Now we need to shift enough points such that the repeating part once again comes after the decimal, but this time we don't need an integer part. We just want to get rid of this part. So to do that, we need to shift it 1, 2 places, where that 100x is equal to the repeating part of 924. Now all we have to do is multiply, and we get that 99,900x is equal to 924, which now we're giving these in integer form. So we can divide both sides by 900, and x is equal to this. So now we have this to be x, and we have this to be this. Now all we have to do is add 32,054 over 100 plus 924 over 99,900. And ultimately the answer you would get is whatever this nonsense is. So 30 by doing cross multiplication, 325.4 times 99900 plus 924 times 100 all over 9990000. So it would be whatever the top is divided by 9,999,000. And put that into the calculator, and you should actually get back 320.54924. Alternatively speaking, I think you could use the repeating part as 492 instead. That probably would have made this a lot easier to calculate. But I guess this way also shows you that you can just always apply this to any repeating part, even if they're not always to the leftmost repeating part or not. Any repeating part works. So now back to more normal looking questions. So now we have to prove that if a real number c is a root of this polynomial, where the coefficients are rational numbers, then it also satisfies the equation of of once again a cubic polynomial, but this time the coefficients are integers. So we have r sub 3 x cubed plus r sub 2 x squared plus r sub 1 x plus r sub 0, and that is 0. We can rewrite this, since if we remember, a rational number can be written as a over b, where a and b are integers. Let's make this a sub 3 over b sub 3 x cubed plus a sub 2 b sub 2 x squared plus a1 b1 x plus a0 b0 is equal to 0. We can make this into a fraction because once again we can apply the multiplication principle of fractions, which is basically you multiply for each term, you multiply the numerator by all the other denominators besides its own denominator. So we would get a sub 3, b sub 2, b sub 1, b sub 0, x cubed plus a sub 2, b sub 3, b sub 1, b sub 0, x squared plus a sub 1, b sub 3, b sub 2, b sub 0, x plus a sub 0, b sub 3, b sub 2, and b sub 1 all over b3, b2, b1, b0, and this is equal to 0. So, but by the zero principle multiplication, we can multiply 0 by b3, b2, b1, b0, and cancel out the numerator to get the top part is equal to 0. But since the coefficients are just products of integers and the subspace of integers is closed under a scalar multiplication, that means the product of these are all integers. So what we can say is that we can say we want to prove that n sub 3 x cubed plus n sub 2 x squared plus n sub 1 x plus n sub 0 0. So we can say this is n sub 3, this is n sub 2, this is n sub 1, and this is n sub 0. And this is indeed in the form that we are trying to prove. Hence, we have proved the assertion that if a number c, let's just substitute c for all x's here, if this satisfies it, then yeah, then it also satisfies an equation of this form. Now for the final problem of recitation, for problem number 37, we once again have to find a mistake in the proof. And the proof is that the proof that they give us is that suppose R and S are rational. By definition of rational, R is equal to A over B for some integers, and they're saying that S is also equal to A over B for some integers A and B. Then R plus S is equal to 2A over B, which, since the product of two integers is an integer, and B was already defined as an integer, then this is clearly rational. But the issue with this is once again the same issue. It looks like they are generally defining rationals, but the thing is that once again they're using the same variables to define two different rationals, or what is supposed to be two different rationals, but ultimately they utilize the same variables. So ultimately, by defining R, you're limiting S to be equal to R. And similarly, if you define S, you're limiting R to just be equal to R instead of any integer, any rational number within the set of all rational numbers. So this is essentially kind of like a half proof by example. And this is not good because it doesn't cover all cases, all combinations of two rational numbers, let's say. So the correct way of doing this would be to say, okay, let R equal to A over B, and S is equal to other number C over D, because since C and D are not defined, they can arbitrarily be any other number in the set of all rational numbers. So this does generally cover all the set of all rational numbers. So then if we do the sum here, then this will be AD plus BC over BD, and this will be equal to R plus S. And since we know that the subspace of integers is closed under multiplication and addition, then we know that AD plus BC is an integer, and BD is an integer. And since this is expressed as ratio of two integers, that means that R plus S is rational. And that covers all the materials of Recitation 4, where we went over the definition of direct proofs and a lot of examples as of how to apply methods of direct proofs towards problems, how to, say, recognize mistakes in proofs, and what are some practices in proofs, and also to be able to reword problem statements in our proofs and whatnot, and really understand, like, say if we were trying to read someone else's proof, understand what they're trying to say, and the language of proofs in general. So that concludes Recitation 4. Once again, I am sorry that I could not make it this morning due to the weather conditions. My email and office hours are always available for anyone who requires any help, etc. And there's also the Piazza post as well. If you ever have any questions, post on Piazza, where any TA can answer your questions. But other than that, I have my office hours, my email, and I hope to see you guys there or maybe next week. Thank you.